Welcome back, my name is Jesse, I am a tutor in Melbourne and I also make a bunch of GAMSAT videos. Today what we're going to be doing is adding a fifth of the Chemistry Crash Course series to the series. I did 4 of them last year, and what are you doing? We've got a helper today. I did 4 of them last year and realized that I left off Redox Chemistry. I did a little bit of Redox Chemistry in one of them, said it wasn't that important. I still don't think it's all that useful for reasoning, although that's what we're going to focus on today. But these series are all about kind of helping people with a non-science background, or people who haven't done this topic, or people who have but need to brush up on it, specifically for the GAMSAT, right? So we are going through mostly like points of theory, but I only cover the things that I think are actually relevant to help you navigate the exam. This is not to say that the exam will actually ask you to do these exact things, but more so these are the background ideas that you can use to kind of navigate the questions, problem solve really quickly without having to kind of get up to speed and learn from the STEM at the same time. So we'll just dive right into it. So basically, as a bit of a content, as I did in the previous ones, what is a redox reaction is the first thing we're going to start with. Then we're going to look at oxidation numbers, how to calculate them. This is one a lot of people have questions about. And then using this to identify redox reactions when they're occurring. The electrochemical series and half cells and relative strengths of different things, different measures. That is probably where we'll spend most of our time, because that is where the true kind of problem solving, logic, reasoning really comes in. Then standard cell potentials, how to calculate them, how to apply it with organic redox reactions, really nothing's all that different. Then predicting spontaneity, which is something we've seen before in some of the practice material. And then the Nernst Equation is more looking at mathematical proportional reasoning. Maths is becoming more and more a popular skill in the test, and it's something that a lot of people aren't as familiar with. So although it is chemistry content, we're going to be looking at it more so as how to draw out a lot of mathematical relationships and ideas from it so that you can actually work with it more generically or more flexibly. Same thing with Faraday's law as well. We'll look at that and how the mathematical relationships that it proves actually is supported by the theory that we go through. So, first of all, what is a redox reaction? I might get some free space here. So we're going to start with that. And what is a redox? So it's kind of in the name. You've probably already found this if you have been searching this topic before. It's made up of 2 different half reactions. So we have reduction reactions and then we have oxidation. So put them together and you're going to get redox. So importantly, they don't really work in isolation. They work in pairs. One kind of pushes or pulls the other. So it's kind of like a cycle in a way. And so the idea is that reduction can be defined in a few different ways. The kind of classical way to define it is a decrease in oxidation number. But we're going to come back to that because we haven't yet done oxidation numbers. The other way that you can identify it, though, is you can also see it as a gain of hydrogens, right? This is more for the organic reactions. The other one in organic is, well, actually, no, not that. And then the other one is for inorganic, you can also just see it as just gain of electrons, right? Really, though, I'm putting these words above it. It's not that an inorganic reaction doesn't have this. It's just that, generally speaking, hydrogen counting is the way we kind of predict things in organic settings. Whereas electrons are a little bit easier to trace in inorganic settings. But all of this is happening regardless in a given reduction, regardless of the setting. So then with oxidation is going to be an increase in oxidation number, which also represents a loss of hydrogen and therefore a loss of electrons. So if you lose negative charge, then the oxidation number, which is not the same, but we can think of it as kind of like a charge state, is going to go up. The other one, I realized I was forgetting something, is you can also track oxygen. So reduction can also be represented by a loss of oxygen. I'll put OX. And then down here, oxidation is gain of oxygen, like that. So these are all different ways that we can identify what redox is. In terms of like real life, what is redox, right? So you can look at, probably the most classic example is rusting. So rusting is a form of oxidation where if you have something like iron comes into contact with oxygen, it then forms iron oxide, right? And so we can balance this. You don't really need to know how to balance equations in my mind, I don't think. So we get this thing here. This is our iron oxide. this is an example, and then this is effectively what we talk about when we're talking about rust, like that, right? Really all it is just transferring electrons. So you'll notice that given that they're actually happening in pairs, you'll see that, like here, for example, going into oxidation numbers, the oxygen went from 0 state to 2-, so it overall reduced its oxidation number. The iron went from a 0 state into a 2+ state, so it increased. And you can see there's that pair. One thing goes up, one thing goes down. In all of that, why is that? It's because there's a loss and gain of electrons. So really, if you want to think about what's happening in redox, you've just got an exchange of electrons, is all that's happening between the two parts. That's the key thing. And this is going to cause those changes in oxidation state. So coming back up, the next thing that we have is oxidation numbers and how to calculate them. So the classic way that we calculate them is, I'll just put oxidation numbers, is we make certain assumptions. So the assumptions of oxidation numbers are going to be, number one is if it's a pure substance, and what this means is any substance or compound that has only one element in it. So things like, for example, oxygen gas, hydrogen gas, ozone, I guess, all these kind of things. Then, although ozone's not the best example, I'll leave that one out so it's not confusing. These are all pure substances. Another one would be just iron, right? Pure iron metal. Then what we do is we assume that the oxidation number is 0, right? We assume the oxidation number is 0, and the other type is if it's charged, then what we do is we distribute the charge across each of the individual atoms. So say, for example, we had H2, but it said plus, like that. This would never happen, but let's just say it did. What that would mean is there's an overall +1 charge here, and we're going to distribute it evenly across the two hydrogens. So that would mean that hydrogen is in a +½ state. Theoretically, that can happen. You would probably never see that in GAMSAT, though I've probably chosen a really bad example to start it off there. Again, if, for example, we had iron, this one's a simpler one, it might be in the 2+ state. We take that charge, we distribute it, there's only one iron here, and so therefore we assume the iron is in the 2+ state, right? So these are only referring to pure substances. Most of the time, you'll see neutral, and so you just assume it's 0 charge spread across 2, 3, 1 different atoms, so they all have a charge of 0, they're all neutral. The second assumption that we make is that hydrogens and oxygens, when bound to other things, when bonded to other things, so hydrogen and oxygen, when bonded, are in the +1 and the 2- state, respectively. So I'll put those next to them, +1 and the 2-, or really 1+. It's weird in chemistry, technically you put the number first, but you can just put the charge in front so it looks like a negative number. It's actually easier on the maths anyway. They're never going to know, it's a multi-choice exam. So we always assume these particular states if they're bonded. So for example, classic one would be water, right? If you think about it, we've got 2 hydrogens, 1 oxygen. If I go ahead and assume that the oxygen is in the 2- state, I can see the overall charge, which normally sits up here, is empty, it's 0. So I can make a little equation and say that 2 hydrogens, whatever charge they have, plus an oxygen, which is -2, should add up to 0. So therefore 2H minus 2 is equal to 0, and now I just solve algebraically, right? I can add the 2, divide the 2, and I get +1. And that actually proves the other assumption anyway, right? If we had something that was a little bit more complex, say we had, for example, H2CO3 like this. Actually, I'll do HCO3 because that would be neutral otherwise. HCO3 minus. So let's say I'm trying to find the charge of the carbon. So what I can do, or the oxidation number, so I can assume the hydrogen is in the +1 state. I can assume the oxygen is in the -2 state, but there are 3 of them there, right? And I know that the overall charge is -1. So I go the hydrogen, which is 1, plus carbon, which I'm going to find, plus 3 lots of -2 gives me a total charge of -1. So now I solve it mathematically. So 1 plus C, this will be -6, equals -1, and then I can move everything else across. So I can add the 6 and get 5, and then minus the 1 and get 4. So I end up getting +4. So therefore it's in the 4+ state, like that, and now I've solved it. So you can do that in a given reaction here. This might backfire on me. I'm just going to make something up. So let's say we have iron plus HCO3 minus, and then it's going to go into, and this is not a real thing, so I'm just going to like literally make it up entirely. That probably could work. HCO3, so there, I might do that just to be a pain, and then plus, I'll just put H2O. Might not even be balanced, don't fuss about that. I'm not going to bother trying to create one of those. It's more important, if we're trying to pick up whether or not redox has occurred, just look at the oxidation states. So the iron, we'll do that in pink. It's in the 0 state, right? It's a pure substance. If we find it over here, then what we have is carbonate. Now this is where there's a little bit of memory that is useful here. So knowing some common things like hydroxide is -1, carbonate is -2, and so on is useful, but I would say that it's very unlikely that they would expect you to know those. They would more likely hint at it in another way. So we're going to use that here in this case, but we also know from before, whenever there was carbonate, it was in the +4 state. So +4 here, and then what's this, 6 minus, right? 3 lots of 2, that gives us an overall -2. That's where it's going to come from. I'll get rid of those though. So now we have 2 ions plus, and I'm just going to bundle this together and call it a -2, and it looks to be neutral. So I can solve the iron state. I can add the 2 and then divide the 2 and get +1, like that. So the iron is in the +1 state, so I can see that's gone up. So that is oxidation in that case. Now let's see if I can find something getting reduced. So over here, if I try to build this, hydrogen's in the +1 state, oxygen's in the -2 state, hydrogen, which I know is +1, so +1 plus carbon, and then +3 lots of -2 is equal to -1. This is what we were doing before, so we get +4 for the carbon. Over here, it was in the +4 state as well, so that has not changed at all. And then over here, we assume -2, hydrogen's in the +1, and they've also not changed. So what this means is this would actually not be a redox because I don't have both an increase and a decrease of 2 different species. Again, it's not even necessarily fully balanced. Whether or not that has an impact, I haven't tested it, but this is all you have to do to work out whether or not it's redox. Otherwise, just look to see if hydrogen is being added or lost, or if oxygen is being gained or lost, or if you can actually see the electrons written in there actually exchanging, then you know that it's going to be redox. Those are a little bit faster, but oxidation states are always absolutely foolproof. Okay, so then the next thing is going to be the electrochemical series, which I've got over here. So you might have seen some of these. They have them in questions a lot of the time. They don't give you the full electrochemical series. This one here is actually from the VCE study design, or from the data booklet that Year 12s use in Victoria here. And it's probably the best one because it's very high quality. It's not a grainy image like you'll get off Google Images. So I'll link this PDF below, and you can kind of download it and take a screenshot or something of it and use this one. You would never be expected to memorize it, so don't fuss about that. They would never give you the full thing. They're going to give you a small snippet of it, right? So what we're going to do is zoom in a little bit and have a look at some of the patterns as to how these are traditionally written. So the first thing is, it's just a list of reactions, right? And they're all what's called half cells. So a half cell is just a reaction that is only oxidation or only reduction. It's half of the overall redox, right? And we're isolating them, and you'll notice that every time the electrons are always written on the left side of the arrows, right? So what this means is that the electrons is a reactant, and therefore when you go forwards, you are combining electrons with the other reactant. And so that means that you're gaining electrons, which is reduction. So you'll notice that every reaction is written such that the forward reaction is reduction. And it's a reversible arrow because it is an equilibrium. It can reverse, and the reverse would be oxidation. You'd be freeing up electrons in that case. And so that's why it does show us all of our reactions, and then we can put them together to create full overall redox reactions. Now, in terms of the patterns in it, because that's probably the thing that's most important, we first have to kind of understand some of the language about how we describe things, reactants, as either undergoing oxidation or reduction. So it's a little bit confusing the first time you kind of learn it, but we refer to a reactant like here, fluorine gas, that is going to reduce into fluoride, which should have a little negative. Looks like it just didn't come across very clearly. So much for not being a grainy image. We refer to reactants on the left side as oxidants. And the reason why we do that is because they cause oxidation in the other chemical species that they're in contact with, but they themselves undergo reduction, which I know is a little bit confusing the first time you learn that. Things on the right side, because they can go backwards, they can undergo oxidation and therefore cause reduction in the other species they're in contact with. So they're referred to as reductants, right? Like this. You will never see a left-hand side species referred to as a reductant because it cannot undergo oxidation itself, right? It can't go backwards this way further because there is nothing on that side. So we use those to refer to the left and the right. Conventionally, I'll point out that they can give you the same, subset of the table and have everything flipped around just to mess with you. But for now, we're just going to go conventional. So the next thing is we can talk about relative strength of oxidizing and reducing strength. So an oxidant has a particular amount of oxidizing strength, its willingness to reduce, and therefore its ability to oxidize something else. And the idea is that the higher up you go on the table, the stronger the oxidizing strength. So strongest oxidant, strongest oxidizing strength. Like that. We wouldn't describe it as being weak reducing strength because it literally cannot cause reduction of the other species. So we only use the word oxidizing strength. And as we go down the series, they get weaker, right? So decreasing strength, oxidizing strength specifically, right? And so on the right, we get the reverse, right? So up the top, we've got the weakest reductants. And then therefore, as you go down, you get increasing reducing strength, right? Willingness to undergo oxidation. So what that now means is that the strongest are the ones that are actually furthest apart. So jumping ahead slightly to spontaneity, which is just whether or not the reaction will occur without any energy inputs, I'll get rid of all of these now. If you have to predict spontaneity, all you have to do is just highlight or locate all of the chemical species that are available in the state that they are available. So let's say we have a bucket, and in that bucket we're going to have, dissolved carbon dioxide, which I probably shouldn't use because that's not even in this table. Let's leave that one out. Let's say we have hydrochloric acid, aqueous, and then we also have iron metal, and then we also have tin oxide like this. And what we're going to do is we're going to try and find all of these species. Now, importantly, when you've got something in solution, there's a couple of things. First thing is the hydrogen chloride doesn't mean you actually have hydrogen chloride or hydrochloric acid. You have H+, and you also have chloride, Cl-. Then you've also got solid iron, nothing changing there. Then here, the tin oxide, we assume the oxygen's in the -2 state, right? So we have O2-, and we also have tin, which must be in the 2+ state to have balanced that negative into neutral. And then finally, because it's aqueous, it also means we have water available. So we've got to find all of these things. So let's see if we can find hydrogen, and I might have to zoom out a little bit here. And we can see here, hydrogen ions, right? So we're going to circle it. Then we're going to see if we can find chloride, and we can find it up here. We don't want to circle chlorine because we don't have chlorine, we have chloride. Then we have our iron metal, which we can find here. And then we also have tin 2+, which is up here. And then we have oxygen 2-, which I can't find anywhere. I don't think it appears on this particular one. It does not. Cool. And then finally we have water, and water appears in a few different spots. So we've got it here, here, and further down, here, and here as well. Now you'll notice in this particular one, it requires oxygen. So we're going to block that one out because we don't have oxygen gas available. So even though water's there, this reaction won't go if the other reactant is not there, right? So make sure that it's only that you've got all the reactants for that given reaction. Now the next thing we do is we look for what is the highest thing on the left and the lowest thing on the right, because the left side species want to go forwards, and the higher up you go, the stronger they are, the more willing they are, or the more spontaneous they are. The lower down you go on the right, the more they are willing to go backwards and oxidize. So the highest thing on the left is actually this here, and the lowest thing on the right is the iron metal. And what that allows us to do is predict which reactions will go forwards and which reactions will go backwards. So if we jump down here, this is the reaction that would take place in that bucket. So that would mean, if we write them out, we would have 2H plus 2 electrons converting into, we'll get rid of the double arrow now, converting into H2 gas. And then under here, the iron would be going backwards. So that would be converting into iron 2 plus and 2 electrons. And if we just bundle all of the left-hand side together, we get Fe plus 2H plus 2 electrons, and then we get H2 plus Fe2 plus 2 electrons. Like that, just bring this over. And then we can see the electrons cancel out, right? These are the electrons that are transferring from one to the other. So in that way then, we have iron plus a couple of protons, so effectively acid, converting into hydrogen gas and iron metal ions, like that. And there's our redox. You can see an increase in oxidation number from 0 to 2 plus, and a decrease from +1 down to 0, like that. There's the overall reaction. Being able to build overall reactions, very, very, very unlikely. It's very technical, but that just shows you how you use the electrochemical series to predict whether or not a reaction will be spontaneous. The other thing is that I didn't explain it here because it was a relatively simple example. If the highest thing on the left was still lower than the lowest thing on the right, so say we didn't have the acid, so we removed this and then we removed this. Now the highest thing on the left is the water down here, and it's below the thing on the right. This would be non-spontaneous. It would cost energy to make it happen, and therefore you would get no reaction whatsoever. So as a quick kind of catchphrase, you can always remember that the left species should be over the right species. Usually the way I kind of draw it is I just kind of do this, because that's visually what we're actually doing, and that's the reminder, left over right. Yep. So that's the idea, and this would be reduction at the top, and then oxidation would be the reverse reaction, just like that. Cool. So the next thing is we've been ignoring all of these standard potentials over here. So what this refers to is the amount of energy measured in volts that you actually release when one of these reactions takes place. Because all of these reactions are drawn with the reduction reaction going forwards, these voltages are all assuming the reduction reaction, the forward reaction. So if you were to reverse this particular reaction backwards and oxidize, then you would get a negative 2.87. It would just flip sign instead, right? It would flip the potential. So what that means is, coming back to the reaction that we had, let's go down here and grab these and be fancy. I can, there we go, like that. We had 0 volts coming out of the hydrogen, and then the iron, not negative 0.44, it would be positive 0.44 that it would produce. And so therefore, the potential of the whole cell, of the whole reaction, is reduction plus oxidation. Now this is where sometimes different textbooks explain things in different ways. I'm going to say plus, assuming that you've already flipped the sign on the reverse reaction. So that would be 0.00 plus a positive 0.44. And that gives us a positive 0.44 volts, like that, right? Now, some textbooks, they write it like reduction minus oxidation because they're not factoring in the reversing of that sign, and they're assuming you're just grabbing the numbers from the actual table, and it still works. So that would be 0.00 minus, and then you just plug in negative 0.44 from the table, and that is going to reverse the sign for you, because you'll get a double negative which makes a plus, and you'll still get 0.44 volts. So how you want to think about it is up to you. I usually like flipping it, partly because then it just looks like the sum of all of the voltages combined, and it's also really handy because knowing that is helpful when they write the mini series that they give you backwards, for example. So always check where the electrons are, because they might have given you an electrochemical series and they might say A plus this into B, and then the next one might say C plus this is into D plus 2 electrons or something, and then they'll give you voltages. They'll say this one's 0.37 and this one here is 0.77, and then you've got to look at them and go, well, that one's reduction, that one's oxidation, right? So in order to rank them, they need to be written in reduction form. So this one needs to be reversed, the C and D one. So we would need to flip that around and put D plus 2 electrons into C, and then it would actually have a negative 0.77. And so in a series or in a table, that would sit below the reduction because its potential is below the potential of that one. So now we know the spontaneous reaction would be this one going forwards, left over right, this one going backwards, and therefore if this one goes backwards, we actually get positive 0.77. So E of the cell would be 0.37 from the reduction, and then plus 0.77 from the oxidation. Or you can think of it as 0.37 minus negative 0.77. They both give the exact same result, and then overall then we're going to get 1.14 volts. Like that. That would be the spontaneous reaction, and that would be the amount of energy released, because we know energy release is generally the spontaneous direction because it leads to more entropy. Cool. All right, so that is the electrochemical series. A small thing then is more about problem solving. We've gone through the theory, how do you problem solve it? So if, for example, they said that there are a bunch of things in a bucket, let's keep all the purple ones that we already highlighted, and from those purple ones, let's say they're all present, but then it says, of the list, which of the following will cause no reaction, or which of the following will cause a reaction. So one that won't cause a reaction is anything that is on the left side that is below the thing on the right, right? So anything below iron, right? So basically you could draw a line, and that would mean that any of these species in that particular case would not be able to cause a reaction because the left would be below the right. So you just create a bar or a cutoff, and then you can just see, well, which of the options sits there. If your answer is there, it's your answer. If it's not that, then it's going to be something on the right that sits above the iron. So anything on the right from here, because iron will be the preference to react. So that way then you don't actually have to test and check each of them. You can just find the cutoffs each time and then work out, well, anything below on the left or anything above on the right or something similar, and then you'll be able to see which one fits that. Remember that you won't be working with a series this large, right? Probably 4 or 5 of them in a particular order, and then you would use them like that. Cool. All right, so we've gone through the standard potential, and we call it standard, but you'll notice there's a little E0 on most of them. I was a bit lazy on that one. This refers to standard conditions, right? And that is 1 atmosphere of pressure and 25 degrees Celsius or 298 Kelvin temperature, standard lab conditions. If you change temperature and pressure, often reactions change a little bit, and therefore the potentials that you produce might vary. You're not expected to know how to predict that. There are mathematical equations that solve it, but we're not too fussed about that so much. We generally work in standard values. Organic, so moving on to organic redox reactions. Effectively with organic, I covered probably most of it at the start actually. So if you were to draw out a particular compound, let's say we have CH3, CH2, CH2OH, and then it goes to CH3, CH2, CHO. And we have to work out, is this reduction or oxidation? I'm not going to balance it. All you have to do is just trace it and go, well, what's the same first? So you can see CH3, it's all there. Then we had a CH2, yep, it's all there. CH2OH, CHO, there's the difference. So let's investigate what the difference is, and we can see that there were, here, we had 3 hydrogens, 1 oxygen and 1 carbon. Over here, we have 1 hydrogen, 1 oxygen, 1 carbon. So the big difference is we lost 2 hydrogens, and loss of hydrogens is the same thing as oxidation. So pretty much you can just count your hydrogens, count your oxygens, and then you'll know if it's going up or down, and then you can link it to being oxidation or reduction. Cool. And spontaneity, I actually went ahead and already covered spontaneity, and now the math stuff. So the Nernst equation for proportional reasoning and Faraday's law. So you can see we're mostly talking about exchange of electrons. So the Nernst equation, you do not need to memorize this, right? It's come up in questions before. It's handy to play around with, but you definitely don't need to memorize it. So this is for non-standard conditions. You can still get the E or the cell potential or voltage. Let's just call it voltage. So it's the E naught that you get from the table, but then it's take away RT on usually ZF, and then natural log of the reaction quotient. So this is just from the table, and then we've got a few constants here, right? So we've got R, which is our standard constant 8.314, depending on the units that you're using. You don't need to know the number though. F is going to be Faraday's constant, which is 96,500. Z is going to be the number of moles of electrons per mole of reactant. So really what that refers to is in the half cells, you would have noticed that we had things like this. So it's referring to this number, right? It's the coefficient of the electrons. In fact, I might actually put that, it's probably a little bit easier. Coefficient of electrons. It's not an actual number of moles in that, like, it's not like 0.35 or something. And then T is going to be temperature, and that's always in Kelvin. And then Q or QC is the reaction quotient. And so remember that in general terms, this is more like equilibrium. It's the reactants, it's the product concentrations divided by the reactant concentrations raised to the power of their coefficients, right? I'll just put A and B, but we're not going to fuss too much about that. We don't want to get into the actual theory of the formula. We want to look at what it tells us and whether or not it supports the work. So first of all, it says you start off with a standard cell potential, but if temperature is varying, then you will get an adjustment. And you can also get an adjustment based on the concentrations or the relative concentrations of things and whether or not it's achieved equilibrium at that point. So let's just start with investigating the effect of temp, right? So if we were to increase temperature, what does that actually do to the overall cell potential? You would first look at it and you might think, well, T's on the top, so maybe it's going to increase it. But you'll notice that it's on the top, but it's on the top of a number that is going to be subtracting from the E. So if we trace this, if we increase temperature, we're assuming that all the others are holding constant. This whole block is going to get bigger now as a result of that increase in temp, which means that we're taking away a bigger number. So if you take away a bigger number, you actually get a smaller cell potential. So now we know that increasing temperature equals decreased E of the cell, like that, right? Another example, probably should have copy pasted it, is let's look at what happens if we change the mole ratio of the number of electrons. So ZF, LNQ. So in that one, it would have the reverse effect, because if we were to, say, increase the number of electrons transferring, that's going to decrease the value of the fraction and therefore decrease the value of this whole thing. If we take away a smaller number, we end up with a larger result. So therefore, increasing Z equals increased E, right? Generally speaking, not to say that one species would produce a greater voltage, because they all produce different voltages, but relatively speaking. Realistically, Z would actually be a constant for, any particular temperature and pressure conditions. So it's a bit ridiculous to even talk about that one. but we want to just look at it very abstractly just for the maths. Now let's look at Q. So we know that when Q is less than K, we know that the reaction is what's called to the left of equilibrium. In other words, what that means is that it's still progressing forwards. It's still favoring the forward reaction. So if that were the case and it implied that the reaction had not yet equilibrated, then you know that Q is lower than it normally is, right? So what happens in that case? E equals E naught minus RT on Z, F, L, and Q. If we were to decrease Q, or make it lower, right, than normal, that decreases the value of the log. All of this is constant, so therefore this whole block gets smaller, and if you take away a smaller number, you get a larger E. So what that means is that in terms of a reaction progress, if K is sitting here, and the reaction starts over here, and finds its balance point here, and it might overshoot and shoot back like that. The idea is that at this point, anywhere to the left, this is position 1, and we'll call this over here position 2. So that would mean that E in this position is greater than E2, and this would mean over here, E2 would be greater than E1, and then at this point, this would be when E is equal to E naught. Like that, when it's at its equilibrium position in most cases. Cool. And then finally, the last one we had is Faraday's law. So Faraday's law is written in a couple of different ways. So one of them is, you can say that charge is equal to IT, but you can also say that charge is equal to the number of moles of electrons multiplied by Faraday's constant. So it's a pretty simple law actually, and it just says the more electrons you're transferring, the more charge you have, right? And this, remember, is a constant. So there's a direct proportionality there. We can see that charge is directly proportional to the number of moles of electrons. Now, what we could do is look a little bit more at where the number of moles of electrons comes from. If we have two different half cells, so we have Fe2+, it transfers 2 electrons for every run, and then we'll have another one that's just like, let's see, we'll do cadmium, I'm just going to call it +1, plus an electron, like that. So they're both reduction. So which one is transferring more charge? If we had the exact same amount of each of them, let's say we have number of moles of Fe2+ is going to be like 0.1, and the number of moles of cadmium plus is going to be 0.1 moles as well. Even though they have the same number of moles of metal, they have different numbers of moles of electrons. We can see that the number of moles of electrons for this one is going to be 2 for every one, so it's going to be twice as much. And over here, number of moles of electrons is going to be, it's a 1-to-1 ratio, it's going to be exactly the same, 0.1 moles, like that. So in terms of which one transfers more charge, the one that transfers more charge is the one that transfers more moles of electrons. So therefore, the charge transferred or associated with iron will be greater than the charge transferred in cadmium. In fact, we know that by proportionality, it'll be twice the charge of cadmium, like that. And that could become an answer. You can see that we're not as interested in the chemistry, more so interested in what kind of statements or conclusions we could make based on that information. There we go. So even though it's a very rapid run through all of redox chemistry, chemistry that is relevant to the actual GAMSAT, this is really as far as I could see it ever stretching. It's otherwise a very technical topic. I've seen like people putting together questions, like I've seen preparation material that has questions and it literally just has like beakers with half cells and it's saying what's the anode, what's the cathode. That's like high school chemistry. It's very, very technical. There's no reasoning in it. It's all based on memory. They're not going to ask that, you know, and if they were to set something up similar, they would probably give you a decent enough explanation to work with. They more prefer to look at predicting reactions, looking at whether or not things will react with each other, and a lot of that comes from the patterns in the actual electrochemical series. So hopefully that gives you a really rapid rundown of exactly how it all works. Hopefully it's been clear. Let me know in the comments if there's anything else that was not clear. Otherwise, keep studying, use this to do your questions, work through it in bits of 5 minutes. Probably should have said that at the top. And yeah, hopefully this has clarified it, and that now puts a proper wrap on the Chemistry Crash Course series. All right, I'll see you guys in the next one.